Rational functions are functions that have a fraction bar, like r of x here, and they're typically a polynomial over another polynomial. Polynomials have all numbers in the domain. There's no issues with them. But when division is added, we must not allow for 0 in the denominator. To find these numbers, all we need to do is factor the denominator and find the zeros. We do have to factor the numerator as well, because that will affect what kind of zeros the denominator gives us. And the zeros in the denominator that we find, these must be excluded from our domain. For this polynomial, or I should say this rational function, we're going to factor the polynomial parts and see what we get. In this top part, we have, I can take out a 6. That gives me x squared plus x minus 6. In the bottom, let's see, we can try factoring by grouping here. Out of the first two terms, I can take out a 3x squared. That gives me x plus 5. Out of these two terms, I can take out a negative 12. That gives me x plus 5. Yep, x plus 5 and x plus 5. Yep. And so now I can take out the x plus 5. And that leaves me with 3x squared minus 12. I can take out a 3 from the 3x squared minus 12. That gives me, I'm just going to write this 3 in front. That gives me x squared minus 4. And that's a difference of two squares, which will give me x plus 2 and x minus 2. That's all in the denominator. And now we can look at this numerator one. And the numerator, we can look at the AC method. Let's try A is 1, and then C is negative 6. 1 times negative 6 is negative 6. B is just positive 1. Two numbers that add to give, or multiply to give negative 6, add to give negative or positive 1. That's going to be negative 2, positive 3, I believe. Negative 6, and yeah. And since A is 1 here, we can immediately factor this thing down into x minus 2, x plus 3, and then the denominator is still the same. So I have the numerator and the denominator factored, and we must at this point exclude the zeros from the denominator. That gives us, this one right here, gives us x cannot equal negative 5. This one here gives us x cannot equal negative 2. And this one here gives us that x cannot equal positive 2. We can use these zeros to find the denominator. So it would originally be negative infinity to infinity, but we must exclude these. So we can do that by just writing negative infinity up until negative 5, and uniting that with negative 5 up to negative 2. Uniting that with negative 2 up to positive 2, and finally 2 up to infinity. This is the domain of the rational function r of x. Now, there's still more to note from this thing, though, because when we look at this function here, we can notice that there's actually things that we can remove, namely the x minus 2. Of course, the 6 can be reduced down to 2, but that's kind of a minor thing. And so what we actually get is 2 times x plus 3 over x plus 5, x plus 2. Now we have to exclude the positive 2, even though it gets removed by the division. That's because we still have a 0 in the original problem, the original one that's given to us, r of x here, this one. This still has an issue with x equal to 2. It'll give us 0 in the denominator. So any value of x that gives you 0 in the denominator, that gets removed when you simplify it, like we did here with x minus 2. These are called discontinuities. They're called like holes or jump discontinuities typically. Normally removable discontinuity is a good word for it. But the rest of them, the x plus 5 and the x plus 2 giving us negative 5 and negative 2, these are what give us asymptotes. And these are a very different kind of discontinuity. Here's the function that we just had, r of x, graphed here. And you can see it's an interesting looking function. It's got these weird, just kind of like weird behavior. But what you'll notice is that we have the two asymptotes at x equal to negative 5 and x equal to negative 2. If I plot these things, they are vertical lines. And you'll notice that the function, as it gets closer to the asymptote on the x-coordinates, as the x-coordinates get closer and closer and closer and closer, they actually shoot, in this case, they shoot downwards to negative infinity. On the right-hand side, it shoots upwards to positive infinity. And the same thing happens with negative 2. It shoots down to negative infinity there, and then up to positive infinity there. That's what asymptotes do. The function blows up or blows down to positive or negative infinity as x gets closer and closer to the value. Here you have the function graphed. It's the exact same thing. And whenever you draw an asymptote, if you're going to do it by hand, it's a good idea to draw it with a dotted line. That's because there's no part of the function that actually evaluates on that line, but the dotted line kind of symbolizes an asymptote. And what you'll see here that I have on the right, I have x and then the arrow, and then negative 5, and then a minus kind of in the power of a negative 5. What this is literally saying is x approaches negative 5 from the left. If you think about the axis, right, we have this way goes to negative x, or negative infinity, I should say. I'll say negative infinity. And on this side, this approaches positive infinity. So it's kind of natural to have the idea that negative is the left-hand side and positive is the right-hand side. And that's what we use for this type of what's called a limit. As x approaches negative 5 from the left, on the negative side or the left side, the function r of x, well, as x approaches negative 5 on the left, right, x is getting closer and closer and closer to this value on the left-hand side. Well, the function approaches, it just shoots down towards negative infinity. So r of x just goes to negative infinity. So I can ask a similar question. As x approaches negative 5 from the right, the function r of x, well, as x gets closer and closer and closer to negative 5 on the right-hand side, the function shoots up to positive infinity. So it goes to positive infinity. Finally, as x approaches negative 2 from the left, the function r of x, right? Let me just kind of erase some of these lines so they don't get confusing. We're going to here on the x-axis, the function shoots down, right? As you get closer and closer, you get just higher and higher values. Or sorry, I just say lower and lower and lower values because the function is going to negative infinity. I should also rewrite this. The function never equals infinity. Only a limit can equal infinity. So that's the reason why we use arrows here, not equal signs. So this is what asymptotes do. These are specifically vertical asymptotes. Rational functions will sometimes also have what are called horizontal asymptotes. To find the asymptotes, you can find either vertical or horizontal asymptotes. Typically, there is one more type that we'll look at next, but for vertical asymptotes, it's where the rational function has a 0 in the denominator that is not removed from simplification. So like in the previous one, the previous rational function we had, we did remove one of the zeros. That is not a vertical asymptote. the ones that remain after you do the simplification, those are vertical asymptotes. Horizontal asymptotes are kind of the same idea, except there's only going to be one in the rational function. And the way you find it is you have one of three cases. So first off, a rational function, we're going to designate the letter m to be the degree of the polynomial in the numerator, and the letter n to be the degree of the polynomial in the denominator. So for instance, if I had a rational function that looked like this, let's say we had, I don't know, x to the 6 plus x plus 1 over x to the 5 plus 3. M would equal 6 because the degree of the top polynomial is 6, and n equals 5. The highest power in the denominator is 5. So if m is greater than n, like we do have in this example I just showed you, there's no horizontal asymptote. There is a different type of asymptote that we'll talk about next called slant one, or potentially a more complex one. But there's no horizontal one. Now, if they're the same, so for instance, if I change this and say, I'm going to write 5 on top, and I'm going to make this 3x to the 5th plus x plus 1, and then 2x to the 5th plus 3. In this case, both m and n equal 5. Then it says the horizontal asymptote is at y equal to a over b. And a and b are the leading coefficients in the respective sides of the polynomial. So like in the numerator, the leading coefficient is 3. That's because the highest power is 5, is x to the 5th. So the leading coefficient is the coefficient in front of the degree term, x to the 5th. So 3. So in this case, we're going to have y equal to the leading coefficient at the top is 3. The leading coefficient on the bottom is 2. So y equal to 3/2 is our horizontal asymptote. Y equal to any number, that's just a flat line located at whatever that number is on the y-axis. So just draw a horizontal line from that point. And if I were to rearrange this polynomial around a little bit and say on the bottom we say x to the 4th plus 26x minus let's do like minus 6x to the 5th. Here again, the degree on top is 5. The degree on bottom is also 5 because that's the highest power. Then our horizontal asymptote for this rational function is going to be the leading coefficient on top is 3. The leading coefficient on bottom is -6. It's not 4, it's not 1x to the 4th or 26x. It's -6 because that's the number in front of the degree term, x to the 5. It's always going to be the number in front of that, no matter where it's located. And of course, this can reduce down to -1/2. So that's how you can find the horizontal asymptote for similar degrees on top and bottom. Finally, if we have a degree on top and bottom that the power on top is lower than the power on bottom, so in this case we have a degree on top of 4 and the degree on bottom is 5, then that means it's always y equal to 0. That is the horizontal asymptote for all of those cases. It can be 1 less, like in this case, it can be 2 less, it can be, just a number, so like 1 over that thing, then y equal to 0 will be the horizontal asymptote. And if you look back at our function, we have r of x equal to, let's see, what was it? 2 over x plus 3 over x plus 2, x plus 5. If you were to expand this out, this is going to be a degree of 1. And on the bottom, if you were to multiply it all out, you'd see the degree on bottom is 2, which means our function here would have been or will have a horizontal asymptote of y equal to 0. And let's see that on the graph. If I just draw y equal to 0, and in purple, it's maybe is a better color for it, that just more bright, orange, green, yeah, green's good. You can see that as you go out towards x, to negative infinity in this case, the function gets closer and closer and closer. The green line is the asymptote. The red line is our function. It's getting ever closer and closer and closer. It's going to take a long time. If you go really far out, you're going to see it's going to get really, really close, and you have to zoom in more. Going back to the original thing, if I go to the positive side, as x gets very, very large, the function gets closer and closer and closer to 0. It will never cross the asymptote. Both horizontal and vertical asymptotes will not be crossed, except horizontal asymptotes can be crossed, like right here, -3, 0. It can cross kind of in the middle of the function, but as you get further and further out, this thing will never cross it. It will never go up above. It's always going to be below. No matter how far I go out, it may seem like it's going to cross it, but it's never going to. You can keep zooming in, and there's always going to be a space in between the red and the green. And the same thing is true going out to positive infinity. No matter how close it gets, you can zoom in, and you'll find a space there. For this problem, all we want to do is find the asymptotes. We find the asymptotes for rational functions because they define most of the behavior. There are some caveats to that, but in general, they're really good to find. The first thing we really need to do is factor. That's how we can find the vertical asymptotes. So on top, let's try the AC method. We have A is 4, C is 2, so 4 times 2 is 8, B is +1, two numbers that multiply to give 8, add to give +1. There are none that do that. So we can use the quadratic formula, and that will find us an answer there. I'm guessing it's going to be complex, so we're going to hold off on that for a moment. In the denominator, you can write 3y squared plus 1 squared. So it is a sum of two squares, and that means it's prime, meaning it cannot factor down across real numbers. It can across complex numbers. But because our graphing system is the real number plane, we can't graph complex numbers anyway, so they're just not going to show up on the plane. Therefore, there is no vertical asymptotes. Now, there is a horizontal asymptote. The degree on top is 2, so m equals 2. The degree on bottom is also 2. So that means that the horizontal asymptote is at y equal to the ratio of the leading coefficients. Because the degree is the same, that means you take the ratio of the leading coefficients. On top, that's going to be 4. On bottom, it's going to be 3. So we have 4 over 3. Now, let's take a look at this graph. This blue line is the horizontal asymptote that we found. And this first one, this is the rational function we have. Let's graph it. It's kind of odd because there's no vertical asymptote. And normally there are vertical asymptotes that you deal with. But there is a horizontal asymptote that it does satisfy, right? If I go to the left, it gets closer and closer to the blue line, but never crosses it. It does cross here, right here, but that's because it's kind of in the central area. As you go out to positive and negative infinity, it will never recross the asymptote. It may look like it, but if you zoom in enough, there's always a space there. Also, really quick, I know our function had y in it, and I have x here. That's just because Desmos doesn't recognize y being the independent variable. I just had to use x instead, but it doesn't matter the variable. It's just whatever variable is written. As I said before, some functions do not have horizontal asymptotes. That's the case when m is greater than n, like we have here. M is 3 and n is 2. When this is the case, we have a different kind of asymptote. In this case, it's called a slant asymptote, but if the degrees are more than one step apart, like here we have 3 and 2, that's one step apart. If it's more than that, it's going to be kind of more complex asymptote structure. But in this case, it's going to be a slant asymptote, and these can be found by using polynomial division. So let's set that up here real quick. 4x cubed plus 3x squared minus 12x plus 15. We're going to have to use long division for this because the denominator is not in a simple linear form. But it's not going to take too long because it's only one step apart. 4x cubed divided by x squared. This gives us 4x. Multiply it through. We get 4x cubed. 4x times -3 is negative 3x. Negative 12x squared. 4x times -1. Negative 4x. And of course, subtract 0. 3x squared plus 12x is going to be 15x squared. And then negative 12 plus 4x is going to give us negative 8x. Bring down the next term and do the division again. 15x squared divided by x squared. Just going to give us 15. So multiplying that through, we get 15x squared minus 45x minus 15. Oh, there's an error in here. We have 4x times, this is supposed to be plus 1 here. 4x plus 1 gives us plus 4x. And negative 12 minus 4x gives us negative 16x. And now we can continue still doing the same thing. 15 in there, 15x squared. 15 times -3 is negative 45x still. And then 15 times 1 is plus 15. We can subtract these. And that's going to give us 0 here. It's going to make this one positive. And then make this one negative, of course. 45 minus 16 will give us 29x. And then the plus 15 minus 15 gives us 0. So this thing can actually be rewritten as 4x plus 15 plus 29x over, the divisor is still the same denominator there. And this bit is the slant asymptote. It's just a line, and that's why it's called a slant asymptote, because a line is just some kind of slope, and a slope is like a slant. So if we graph this thing, this 4x plus 15 is going to kind of dictate some of the end behavior of this rational function. Okay, here is the rational function graphed, and this is our slant asymptote, the purple. And right now, this looks a little bit weird. There are some stuff here, but the way it is, I'm going to actually change the Y scale so that it's a little bit easier to see. Sometimes this is helpful for, you know, in your own work. If you change some of the scales, it can be a little bit clearer what we're looking at. I'm going to make 10,000 or just 1,000. And here we see more of the usual rational function behavior. There's some vertical asymptotes that we didn't find. I was just trying to find the slant asymptote here. And this purple line is the slant asymptote. And as you can see, as x gets very, very big, the function gets closer and closer to this purple line, but it never crosses it. It gets closer and closer and closer. We'll never cross it. The same thing is true if I go back to the function and now go to the left-hand side. You can see that this function gets closer and closer and closer. The scale changed, that's why it's not the same kind of angle as the previous one, because I hit the default zoom button, but it's still the same function. And you can see that it gets closer and closer, but never crosses it, as you would expect from an asymptote. A drug's concentration when it is injected into a person's bloodstream can be modeled using this rational function. C of t is the concentration in milligrams per liter. and T is the time in hours after the drug is injected. Because this is a physical application type problem, T less than 0 doesn't make much sense because that's kind of like back in time. So we're only really looking at T greater than or equal to 0 here. Now there's a few things we can look at in this graph of this rational function. Namely, probably one of the most important things is understanding like different points, how concentrated is the drug. So like, for instance, if we're trying to figure out what is it 3 hours after the drug is injected, then we have 5 times 3 over 3 squared plus 1. 5 times 3 is 15, 3 squared is 9, plus 1 is 10, and this is 3 halves, or in other words, 1.5 milligrams per liter. And because this is a rational function, right, we can understand the asymptote here. There is no asymptote from vertical asymptotes from the denominator, because this is again a sum of two squares, so only complex numbers are going to be the zeros. But the horizontal asymptote, the degree on top is 1, so m equals 1. The degree on bottom is 2. Since the degree on top is less than the degree on bottom, y equal to 0 is the horizontal asymptote. And this is what you would want, because after a very, very, very long period of time, you would expect the concentration, so let me say it like this, as t goes to positive infinity, you want the concentration of the drug to go to 0. And that's what this function does do. The asymptote goes to 0 because that's the horizontal asymptote. Let's take a look at the graph just to show the point. So here is the function graphed. And again, we're not considering, we're not worried about anything less than 0. That doesn't make sense for a physical application involving time. And you can see it kind of spikes in the beginning. I guess that's where like the drug is being distributed all throughout the body. And then as it gets absorbed in and then breaks down or whatever it does, it slowly decreases. And as it goes out to infinity, I mean, t is in hours, so 72 hours, this is 3 days. It's at 0.069 of what it was before. Then if we look at 168 hours, that is a week. You can see it's very, very low concentration. Yeah, it's 0.029 milligrams per liter. So it's extremely small compared to the first initial bump there.